All right, I'm going to solve problem number 6 on the practice test. We are given a two-state quantum system with basis vectors E1 and E2. The Hamiltonian in this system we're not given any information about, but we do know that it has eigenvectors 1 and 2, and with energy eigenvalues 10 h bar omega naught and 5 h bar omega naught. And we're given the eigenvector 1 in this E1 E2 basis is here. So to find 2, the other normalized energy eigenvector, we know that 2 is going to look something like in the E1 E2 basis is going to be some linear combination of E1 and E2. We just need to figure out what are these two pieces. Let's guess A and B. So to solve for these two unknowns, we need two equations, and that is going to be given by the orthonormality of 1 and 2. So 1 on 2 should be 0, and 2 on 2 should be 1. So 2 on 2 I think we recognize as if we take the inner product of 2 with itself, we get a squared plus b squared. We know that's the normalization condition. So what is 1 on 2? Well, we can rewrite that taking the Hermitian adjoint of 1 looks like minus I over root 5 times the bra E2 plus 2 over root 5 times the bra E1, and we'll let that act on our unknown 2. So A E1 plus B E2. And I'll come down here to the next line. So 1 on 2 then is minus I times A over root 5. And then when, oh, actually look, I did it wrong. E2 on E1, that's 0. E2 on E2 gives us minus IB over root 5 plus, when E1 hits E1, I get a 2A over root 5, and in E1 it's E2, that's orthogonal. So this is plus 2A over root 5. So that must add up to B equals 0. We can cancel the root 5s, and I get that 2A is equal to IB. And so if we can just kind of arbitrarily pick A as 1, then that means that B would have to be minus 2I. So if A is equal to 1, then B is equal to minus 2I. And then we need to normalize this and do the normal process, so I think we'll need 2 to be equal to 1 over root 5 E1 minus 2I over root 5 E2. Alright, if we did that right, then the inner product of 2 and 1 should be 0, and we've normalized. Okay, so part B. All good so far? Okay, good. So part B then, now we're given some state alpha at T0 is here in the E1, E2 basis, and we're asked about measuring the energy of the system at T equals 0. So what can we get, and what are the probabilities? Well, we know that if we measure the energy, then the possible results are just the eigenvalues of the operator that corresponds to energy. The operator that corresponds to energy is the Hamiltonian, and we already know, while we don't know much about the Hamiltonian for this system, we do know that vectors 1 and 2 are its eigenvalues, and or its eigenvectors, with eigenvalues 10 h bar omega naught and 5 h bar omega naught. So 10 h bar omega naught and 5 h bar omega naught are the possible results, and to find their associated probabilities, what we need to do is rewrite alpha in the eigenbasis of the Hamiltonian. That's the operator that corresponds to the energy, what we want to measure. So 1 and 2 is the basis of the Hamiltonian, so we need to rewrite alpha as some linear combination of 1 and 2. So what are these coefficients, expansion coefficients? Well, we could solve that a couple of ways. I think the best way is to remember that this expansion coefficient is nothing more than the inner product of alpha and 1, and this one over here, the inner product of alpha and 2. All right. So let's find these inner products of alpha and 1. We're going to do that in the E1, E2 basis. We've already got alpha in the E1, E2 basis. We've already got 1 in the E1, E2 basis, so we can find that inner product pretty quickly. So 1 on alpha is equal to 2 over root 5 bra E1 plus negative I over root 5 bra E2. Inner product with alpha, which is I over root 2 E1 plus 1 over root 2 E2. And doing this inner product, it looks like we get a 2I over root 10 plus E2 hits E2, a minus I over root 10. So that's 1 over, I over root 10. That's the expansion coefficient here, right? That's 1 on alpha. To find 2 on alpha, we'll take the inner product of the state we found. So that's 1 over root 5 bra E1 plus, now I'm taking the complex conjugate, 2I over root 5 E2, and inner product with alpha, which was here I over root 2 E1 plus 1 over root 2 E2. And it looks like this term stays, the I over root 10, and when the E2's hit, I get another 2I over root 10, so a total of 3I over root 10. So it looks like in the end our state alpha is equal to I over root 10 times 1 plus 3I over root 10, 2. And therefore the probability of measuring the energy and getting 10 h bar omega naught is equal to the magnitude squared, absolute magnitude squared of I over root 10, which is just 1/10, and the probability of getting 5 h bar omega naught is the absolute magnitude of 3I over root 10, so that's 9 over 10, so 90% chance. All right. Okay, so part C. So far, so good. Okay. Part C, assuming no measurement was performed at t equals 0. In other words, pretend we didn't do this measurement. We just asked what we could get. Write the state of the particle at some future time, t. Well, what seems like a hard problem, we actually did all the legwork for already. To find out how the state evolves in time, we just need to rewrite it in the eigenbasis of the Hamiltonian, which we already did above. So, and we just need to tack on the exponential. So alpha of t is just I over root 10 times e to the minus I t e1 over h bar times state 1 plus 3I over root 10 e to the minus I t e2 over h bar times state 2, where E1 and E2 are 10 h bar omega naught and 5 h bar omega naught. All right. So that's done. That's all there is to that. This actually, if you think about it a little bit, this term, the coefficient, the odds of measuring, if you measure the energy of this state, for example, at some future time, then this coefficient out here is changing as time goes by. And so this state is going to be more and less likely to be in state 1 and state 2, depending on those, this piece, but also this time evolving piece. All right. number part D. We're continuing in the E1, E2 basis. We now have some observable U that's represented by the following matrix, some U naught. Check out that U is already diagonal in this E1, E2 basis. That element right there, what this means to be in the E1, E2 basis is that 0 is actually the E1, U, E2. This is the let U act on E2, and then E1 act on that ket, and that gives you the number 0 out. Okay, so that's what this means to be in the E1, E2 basis. All right, so the question is, what are the possible results of the measurement of U? Well, as always, if we want to know what we can get when you measure something, the answer to that is the eigenvalues of the corresponding operator. So we need to find the eigenvalues of this. Fortunately, it's already diagonalized, so we can just, so therefore these diagonal elements are just the eigenvalues. You could set up the characteristic equation and take the determinant of U minus I lambda and set that equal to 0. You're just going to get 1 minus lambda times 3 minus lambda is equal to 0. Actually, that should be whole thing times should be 1 U naught and 3 U naughts. Anyway, the solutions are just the diagonal elements. So U naught and 3 U naught are the eigenvalues of U, and therefore they are also the things that you could measure if you measured U. Note another thing about this being a really handy thing about this. Since U is diagonal in the E1, E2 basis, that means that E1 and E2 are actually the eigen vectors of U. So U on E1 must be equal to U naught, not mu naught, U naught E1. And U on E2 is equal to 3 U naught E2. All right. So normally you would have to do an extra step. If it wasn't a diagonal matrix, after you find these eigenvalues, you'd have to go through that next step of letting U, the matrix, act on some xy to give U naught on xy and solve for what x and y were. But you're going to get out 1, 0 and 0, 1. All right. Okay, so that's helpful for our next part. Part E, now we're asking if you were measured on the state alpha of t, then what would be the probabilities to obtain each possible result. So what we need to do is take our alpha of t, which we had from the previous page, I over root 10 e to the minus I t times 10 times state 1 plus 3I over root 10 e to the minus 5it omega naught. I need those omega naughts in there. Okay, so it's times state 2. So there was our alpha of t. If we're going to measure u, we need to rewrite alpha in the eigenbasis of u, but we just said that 1 and 2 were the eigenvectors of u. So I just need to put alpha of t back into the E1, E2 basis. Right? And so I have these two components to figure out. What are those two components? Well, they're nothing more than what we did already. There's the inner product of alpha t and E1. Right? And alpha of t and E2. So these are the two inner products we need to do, and we're actually going to do this inner product because we know in the 1-2 basis, I think. So let's give this a try. Alpha of t here is given by this. We don't know actually E1 yet in the 1-2 basis. Decisions. I think that it's easiest to use this formula and this formula from before to find out what is E1 in the 1-2 basis. So let's try to do that really quickly. 2 over root 5 e1 plus I over root 5 e2 is equal to 1, and 2 is equal to 1 over root 5 e1 minus 2I over root 5 e2. Alright, so let's solve these back around to find out e1. So let's solve that. e1 is equal to root 5 over 2 times state 1, subtract root 5 over 2 times I over root 5 e2. So I just moved that term to the other side and divided, and now we can plug that into this equation. So we get 1 over root 5 times root 5 over 2, 1 minus I over 2 e2 minus 2I over root 5 e2 is equal to 2. And I think now we have an equation that just has e2's, 1's, and 2's, so let's solve this for e2. To do that, we can get this. We have I over 2 root 5 with a minus sign, so minus I over 2 root 5 and minus 2I over root 5. Those are all the pieces of that guy. And on the other side is 1/2 1 plus, negative 1/2 1 plus 2. And it looks like this is 4I over root 5 over 2 root 5. 2 times. And minus subtract 4 is a total of, so minus 5I over 2 root 5. Minus 5I over 2 root 5. And so then e2 is equal to root 5 over 5. The minus signs cancel when I divided it over, and I get an I on the bottom. I don't like I's on the bottom, so I'll multiply the top and the bottom by I. So I get minus I, root 5 over 5, 1, plus I times 2 root 5 over 5, 2. You might not believe it, but I bet you that that is normalized. If you start with normalized things, you stay with normalized things. Am I talking too quietly? Can you all hear me? All right, that was a lot of algebra. We're almost done now. We've got to find E1 by plugging it into this equation here. All right, and then we've got 2 inner products to do, so I'm going to need another sheet of paper, but I think we're almost there. So it looks like E1 is equal to root 5 over 2, 1 minus root 5I over 2 root 5 e2, and instead of e2, let's write this whole thing. Minus I root 5 over 5, 1, plus I times 2 root 5 over 5, 2. All right, little algebra here. Let's collect our 1's here. I've got a root 5 over 2, and when I hash these products out, it looks like that's a I over 2. The 2 minus signs make a positive, but those 2 i's might make it negative. Those root 5's canceled, and so I'm left with just root 5 over 10. I think so. Root 5 over 10 times 1 plus minus I over 2 times this stuff. The 2 i's make a minus sign, which cancels with that minus sign. The 2's cancel out, so it looks like just root 5 over 5, 2. All right, and let's get that guy. This is 5 root 5 minus 1 root 5, so it looks like that's 4 root 5 over 10. 1 plus root 5 over 5, 2. All right. Oops, that's E1. All right, so there's our E1, and here's our E2. Let's take the inner product of E1 and E2 with alpha of t, which is written up here, to get our two expansion coefficients. I'll steal a blank sheet of paper. Here was alpha of t, I over root 10 e to the minus 10 I t omega naught 1 plus 3I over root 10 times e to the minus 5I t omega naught 2. And E2 is minus I times root 5 over 5, 1, plus I 2 root 5 over 5, 2, and E1 is 4 root 5 over 10, 1, plus root 5 over 5, 2. All right, and the two things I'm looking for are E1 alpha and E2 alpha. Let's get this one first. This is 4 root 5 over 10 bra 1 plus root 5 over 5 bra 2 on I over root 10 e to the minus 10I t omega naught 1 plus 3I over root 10 e to the minus 5I t omega naught 2. And, oops, none of that was on the page. There you go. So the inner product here really isn't that bad. Only the ones hit each other. So it looks like I've got a 4 root 5, so 4I root 5 over 10 root 10. That doesn't look great, but we'll maybe clean it up a little bit. Plus, times e to the minus 10I t omega naught plus the 2 and the 2 hit, so I get root 5 times 3I over 5 times root 10, so 3 root 5I over 5 root 10, e to the minus 5I t omega naught. All right, that's just a number, right? It doesn't look like a very nice number, but it's a function of time. That it depends on when we measure this thing, right? And this is just one of those expansion coefficients. So if you want to know the probability of measuring probability that u is equal to u naught, the first eigenvalue, that's just E1 alpha of t absolute magnitude squared. So we need to take the absolute magnitude squared of this big thing. All right, and I think what's going to happen is, you can imagine we're going to multiply this times its own complex conjugate, and the complex conjugates will have some plus 10I t omega naughts and plus 5i's there, right? And when the so it's a 4-term thing. This is the if this is the complex conjugate over here, it's going to have e to the plus 10 and e to the plus 5, and this one's got e to the minus 10 and e to the minus 5. There's the numbers out front, which have been conjugated as well. But when the plus 10 and the minus 10 hit each other, you just get out a 1. When the plus 5 and the minus 5 hit each other, you just got a 1. So all that happens is we keep those constants. And then we've got two other cases. When these two hit each other, you get 10 minus 5. So that's going to give us a term that's got an e to the plus 5 I t omega naught times some constant. And the inside product is going to give us an e to the minus 5I t omega naught. So really we just have to find out what is this constant out front. There's two of them, and what goes in front of the plus 5 and what goes in front of the minus 5. So to get the the first constant, we're going to do the thing out front of the minus 10 times its own complex conjugate. So that would be 4I root 5 over 10 root 10 times 4 times minus I. So obviously it's just this thing squared. The i's go away. So that's 16 times 5 over 100 times 10. The same thing happens for this constant. When I multiply it by its own complex conjugate, I'm just going to get a 9 times 5 over 25 times 10. 9 times 5 over 25 times 10. How about this term here with the plus 5? That's what happens when the positive 10, the complex conjugate of this, hits the negative 5, just that term. The I and the minus I and the I gives me a factor of 1, so it's going to be a positive constant. So it looks like I get a 12. Root 5 times root 5 is just 5, so it's 12 times 5 over 50 times root 50. All right, and then this term, I believe, I want to argue, is just going to be the opposite of that. It's going to be the same as that. It's going to be the complex conjugate of this guy times him. So that gives me a minus I, kills the plus I over there, and so we get 12 times root 5 is 5 over 50 times root 50. Oh, I'm sorry, 50 times root 10 times root 10 is just 10. Sorry, that should be a 10. So this one is 12 times 5 over 50 times 10. All right, so I know that looks a little crazy, but I want to do just one little piece. I'm not going to solve the other one. If you want to know the other probability, you can just take 1 minus this probability. Okay, but let's check and see if this makes sense, because do you see that this is e to the plus something plus the same number e to the minus something? That's just 2 times the cosine of that thing, right? So we've actually got a constant here. So let's get a common denominator. I think if I multiply this guy by 4 over 4, 16 fives, what's that? 80 over 1,000 plus 20 times 9 is 180 over 1,000 plus that's 60 over 500 times cosine of 5 t omega naught. All right, and let's just check and see. 80 plus 180, 260 over 1,000. So 26, that's 0.26 plus this is 120 over 1,000. So that's 0.12 plus 0.12 cosine 5t omega naught. So that is the probability of getting u is equal to u naught. This is 0.26 most of the time and goes up and down by that much. The probability of getting u is equal to 3u naught should just be 1 minus the probability of u being u naught. So if we take that 1, subtract this, then that should just be 0.74 minus 0.12 cosine 5t omega naught. And I know we didn't do that out the long way, but I think you would see that most of it goes kind of the same, and so that if you thought about this, as time goes by, here's 0.74 and here's 0.26. Sometimes the odds of finding it in the 3u state are higher, and sometimes it's a little bit lower. This guy's going to be doing the exact opposite of that, right? And so this is what would happen as time goes by. So there are some times when you measure it and you're most likely, there's a 100% chance, or no, not 100%, but it's most likely, so 74 plus 0.12, so 86% chance of finding 3u naught. And then other times when it's 0.74 minus 0.12, there's other times when it's only 62% chance of finding that, right? So at different times you measure it, there's different likelihood of the two results. And scene. Sorry.